Well, thank you, Sumaya. My father was a doctor. I'm not, so thank you for the title. That was an easy PhD. Huh? Well, thank you, Jim. I don't know where he is, but he really set up what I wanted to present here. It's a different type of presentation where I'm going to show the system we've been developing for the last 17 years now. It has more pictures because people tend not to believe how thin pavements, what Jim was talking about. Thinning in the pavement is a paradigm that it's difficult to change. So I want to show some examples of probably an extension of what Jim showed before. Just to show a little bit, OptiPave was a Chilean company that was my father's. He passed away last year, and was bought by Forta for Forta concrete fiber. So just wanted to say that. I never know what to say in these presentations because I've said it so many times. I don't know what the people have heard before. So just wanted to give you a heads up with that. The other thing I want always to show the people that helped us do this. It's very difficult. It looks easy, concrete on the ground, but we had a lot of people helping us in different things. Don't have the time to show them all, but I always want to give the credits to people that helped us through this path. So the first thing I always say, I go around the world trying to sell this technology, is concrete thickness. And I think it's one of the biggest paradigms in pavement design. And I always show this example. So it's very simple. Those two pavements are ports, so they have the same loads on them. And the one on the right is, sorry, it's in centimeters. It's, I don't know how many inches that is, but 15 inches. I don't know how much I calculate that fast, but it's a very thick pavement. And you can do exactly the same thing with 4 inches with concrete bricks. So both are concrete pavements, so why the thickness difference? We use them both for a long time. What changes between those two? Jim said it very well. Now that we have mechanistical approaches, we can actually design the pavements, and you can't separate thickness to slab size because they go together. And that's, I think, it's a great example. If I would tell somebody I'm going to do a 10-centimeter pavement for a port, you probably would shoot me. But we do them all the time. So what's the difference? So the system I want to show you, it's what's in between these two. So basically, how big can the concrete be before it becomes a slab? So this idea was my father's in 2005. So he came up. In Chile, we have a problem. I come from Chile, that we have a lot of curling. A lot, I mean, in some cases, that distance there can be up to 1.5, so half an inch, almost an inch. So pavements cracked all the time. So he came up with the idea, instead of letting it crack, and you have cracked pavements, is what happens if I cut them in between the loads. So he came with that idea, and conceptually, the biggest concrete brick you can have is when you have 1 wheel per slab. So if you make the slab small enough that you only have one set of wheels on it, you reduce the flexural moment on the slab. And with that, you can optimize the thickness. So making slabs smaller has 2 effects. One of them is what I was just telling you, is that structurally, when you calculate stresses on a slab, and you go from 10 inches, and if you make the slab smaller, you get the same stress with, in this particular case, with 6.5 inches. So you have equivalent structures with different thicknesses. And that's because you have to put in the size of the slab. When you think about pavement design, normally you design the slab thickness first and then determine the slab size. I don't know, 24 times the thickness. There's many formulas. But when you look at concrete bricks, to determine the thickness you need for concrete bricks, you have to determine first that it's a concrete brick. If not, you can't do it. So what we're saying is that you have to design the other way around. You should determine the slab size first and then calculate the thickness, which is the opposite to what normal procedures do. So this is the curling. Just to show a little bit of the story. So what happens in Chile normally is that you open to traffic and the slabs crack in 4. I don't want to get into the story of that picture, but that's my father there. The other side of that rope is Michael Darter, and he's shown him this curvature of the slab at 12 at midday, more or less. So the theory that slabs have the tips down during the daytime, at least in that case, was not true. So curling comes into a big issue, and it kind of changes everything when you calculate the pavement. Jerry Holland from Floors has been saying this for the longest time. So these two currents of information have crossed, and we could optimize the design. And lastly, we used, and Dr. Lev Kasanovic to help us with this, is to calculate, to actually calculate properly the stresses on a slab. And just as an example, the same slab, if you just, with the same load, you just cut it in half. In that configuration, your stresses go down from 2.5 megapascals to 0.5. So if you maintain the thickness, you get a lot less stress. One of the things I'm going to show is what we've learned from this, because I think it's very important. So finally, Professor Rossler, Dr. Rossler helped us try this. We did this test section in Champagne in April, really. And we tried different thicknesses, different materials, fiber reinforced, etc. So we could have an initial start with real life information. So what are we recommending? And I think this is pretty important, is obviously smaller slabs. How big? It depends on the traffic. So you have to figure out what slab size you want, and then you can design the thickness. So you have to design for one set of wheel per slab. So the typical size that is half a lane, so half of the truck goes on each side, and somewhere between 5 and 8 feet, something like that. I hope I'm converting right, something there. I'll show you what we've learned about that slab size, how to choose the slab size. Then there's another problem, and Jean said it very well, and the layers below the pavement. The other paradigm in concrete pavements, as I see it around the world, I not only just talk about the US, is that everybody talks about thickness. And the pavement, as well as other types of pavements, it's the whole system that you have to design. Jim showed a lot of good examples. Why so many layers? What are you doing? What are you trying to accomplish with each layer? So one of the things we found out is short slabs they don't bend because of loads, but because we have one wheel per slab or one set of wheel per slabs, they rotate a lot. When you push it on one side, it lifts on this side, and then that thing goes on and on. So it's really important to design the base properly. So we've done 3 things, basically. Granular bases, but we've chosen to have granular bases with low fineness below the 200 sieve. So with that, you don't have anything to erode. We've shown that it works really well, even with high contents of water, free water on the base. And we use geotextiles to prevent fines from migrating from one side to the other of the pavement. Don't want to go too much because of the time. So the other things we've seen works really well, asphalt bases or cement-treated bases. And when we do that, we normally put geotextile between the concrete and the base. Those 2 things have proven to work very, very well. Because at some point, one of the things we learned in the testing in Champagne was that after you go over 8 inches, you don't have stresses big enough for the slab to fail. So it will have infinite fatigue. So after 8 inches in terms of thickness, what will happen to that pavement, it will start eroding the bases. So you have to have non-erodible bases and design it accordingly. Jim said it as well. We're not sealing the joints. All the pictures I'm going to show you don't have the joints sealed. Basically for 2 reasons. Because the base is not water susceptible, we let water in. And we have the theory, I have the theory in the company that joint sealants, a lot of people don't really maintain them. So how much water goes in 5 years after construction, I think it's like if it didn't have a seal. So we might as well design an alternative engineering solution. And that's what we've tried to do here. And the other thing we're using is a very thin saw blade. So the cut tends to be very thin. And with that thin saw cut, stones that go in are not strong enough to break and spoil the joint. I'll show you some pictures of it. So this is accepted now. I just wanted to show you this in ACI 30. It's one of the ways of designing industrial floors. So about CO2. We did a big study. This is just one of the pavements, and I think it goes in what Jim was saying, is that first thing I have to say, it depends project to project. You can't take conclusions from this and apply it somewhere else. It's always different. We did 4 different locations and equations, not equations, the results are different. But just showing you this is a real project done in the south of Chile, and we used the Athena software to calculate the CO2 total emissions. And just very fast, it depends what you're doing, 10-year design, 20-year design, 10 years design that you actually maintain it up to 20 years and design for 30 years. So all the things change. But what's more important is that this is, in this case, the asphalt solution, which was an alternative bid with an alternative solution. So it was 2 real-life solutions. So in this particular case, concrete was a little bit higher. Traditional concrete design. In Chile, we use Ashton 98, which I think is the only country that really uses that. And this is short slabs, what I just showed you. This is short slabs with fiber, and this is short slab with shrinkage reducer in it. So again, I think this fits very well to what Jim was saying. First, you see what you're going to build, and then you start optimizing the material. And you can really lower the CO2 emissions. This is another paper that was, Sherry Sullivan gave me this information. And in this case, something similar. You have 6% of reduction when you use this OptiPave system. And if you add that with a good design concrete mix, you can reduce it up to 6% to the typical design. Again, all these numbers change depending on what you're doing. So where have we used this system? Remember, this is a system for a new pavement. You've done short slabs here in the US, white toppings for the longest time. But this is new, over granular, over cement-treated basis. It's a new pavement. So we've done this in highways, low-volume roads, industrial, urbanizations, parking lots. So just show all those pins. The pins are color-coded so you can see what it is. So you see we've done this solution in many, many countries. Up to date, it's about 16 countries. It's catching here in the US with our partner P&A. It's catching in Europe with our partner over there. Obviously, I live down here in Chile. We have a lot of projects down there. So we have a lot of experience now, and I'll show you some of the conclusions that we've learned in these 15 years. So some of the projects, this is an overlay. It was a very bad asphalt. They replaced it in some places with cement-treated base, and we built 23 centimeters fiber reinforced. And that's wrong, it's not 5,000, it's 10,000 trucks a day. It's 189 million easels. So that's a picture of it. A picture in the very south, just showing the different applications. This is the Houston Home Depot distribution center. We did a seminar 2 years ago. We invited everybody that helped us do this technology, so they all stand it over the pavement. And just to show you performance, this is a distribution center in Santiago. That's a 14-year-old pavement. It's 5.5 inches, and it's working. You see the unsealed joints are working very well. Just for the sake of the time, I'll go over it. So that's another one, a Walmart distribution center. That's a 12-year-old pavement, 6 inches. It's working really, this one wheel per slab really works. In Peru, different places, roads for housing, 3.5-inch pavements, very thin. We've done a lot of these, and parking lots. So if anybody wants to see, I have to warn you, these are very, very boring videos because they just show the pavement. So people at the beginning told me, oh, you picked the only picture where the pavement looks good. So what we did is we're filming all the projects. We have 70-something videos. So if you go to YouTube and put that, if you're interested, you can randomly look at the pavements. They're obviously not new because some of them are 10 years old, but you can have a look at them and see how they're performing. So how does this fit in, the design procedures? We have the old AASHTO procedures, which were basically empirical. 98 is a little different, but based on the same principles. And basically what Jim showed, the best design for me today is by far Pavement ME. It tells you really what's going to happen to the pavement. So what OptiPave is just a small brother of it. We use the same equations, the same principles, the same theory, but we extend it because ASHTO or Pavement ME only designs up to 10 feet. It doesn't do smaller than that. So OptiPave, it's a simpler version of that because that's really complicated, and it goes from 4 to 8 and something feet. So it covers what's not covered in this design procedure. It is the same thing. That's just a screenshot of the software. So it will give you the same thing. It will give you cracking in different places of the slab. It will give you a faulting on the joint and IRI. So what have we learned? And I think this is really important. First, we've calibrated the information. So all these mechanistical design procedures are as good as their calibration. So over the years, we have calibrated with real data. And I'm going to show you some examples. So one of the things is, as Jim was saying, is how precise these new methods are. You see the dispersion between, so what the software predicts is the black line, and all of those dots are real projectiles. So it's not all over the place. It's very narrow compared to the prediction. The software itself has reliability, so when you have, that's a 50% reliability line. So if you have higher than that, you will have to move so that you have X amount of points on the right side of the curve. So the software has been calibrated to work in real life situations. One of the things we had to change, and I said at the beginning, is the faulting problem. Short slabs rotate a lot more than normal slabs. We normally don't dowel them because the joint opening is a lot smaller, so load transfer tends to be a lot higher. So we needed a good faulting model. I'm sorry to show these equations, they're very long, but we changed. So we used the same equation from MEPDG or the Pavement ME, but we had to change it for it to work. We had data, we tried to calibrate the original equation, and it didn't work. So we came up with this new one, which is the same one that we added stuff. We added drainage in there. We added all this part in the incremental part of the equation. And with this new equation, which is similar to the old one, we calibrated the new model. So that's the prediction, so observed versus prediction. And we couldn't, with the older model, we couldn't predict those dots up there. So when you don't have the proper base, it will erode and it will fault. So it's very, very important to design properly the base. With this new model, we can predict, obviously it's not 100%, but we can predict a lot closer if you do a bad design. So if you put something that's wrong, the software will tell you can't do that. And I think it's very, very important. So what's really important when you do a new type of pavement like we had is understanding the failure modes. When you understand the failure modes, you can design properly. Again, Jim said it perfectly. Now that we have better softwares and better models, we can start understanding how they fail, and we know what to fix. The typical paradigm is that people fix pavement, making them thicker. And that's not always the case, especially with faulting. With faulting, there are other things that are cheaper and more effective than just changing the thickness. So one of the things we worried about, and this is part of the iterations in time, was how do we make the base not to erode? So the first thing we said, and at this time, I entered the company at that time, this was my father's idea. First, 5% fines, very low fine content base. The problem with that is that it's very expensive to produce, and it depends where you are. That's not easy to construct and to actually find. So we did some testing, and in 2012, we increased that, the spec that we're promoting, to 8% fines. It seems not too much, but this is much easier to actually get. And the other thing is the thin blade. So that's the typical blade, and that's the thin blade. So we tested, the original one was 1.9, 1/16th of an inch, a little bit more. But because the typical blades were 1/10th of an inch, we tried this, and it tends to work. It works pretty well. So basically what we say now, the thinner the disc, the better, and it can't be more than 3 millimeters, which is 1/8 1/8 of an inch, I think. I don't know. It's 3 millimeters thick. So the theory behind why does the low fine base work? So if you have a lot of fines, the fines will be separating the bigger particles. You put water in there, you push with the slab, water pressure builds up, that water moves the particle. Now you have voids in between the bigger aggregate, and there's a volume change. There's a certain point, and it will depend on the geometry of the particles, that the fines are in the voids in between. So you put water in there, you wash it, and nothing happens. So there's a point where you have low enough fines, the base will not suffer pumping. Just very fast, other things we've learned, have 12 minutes left, 10 minutes left, is IRI. So this is the little book of profiling, I think it's called, and that's the IRI gain curve. So there's two wavelengths that increase curling, 10 meters and 2.5 meters. So if you have the same curling and you have the same curvature on each slab, and you build the slab 2.5 meters or 1.8 meters, IRI will almost be double just by that 2 feet different. We learned this because we designed a 2.4 meter project, and IRI was crazy high. So we started investigating. So one of the things we learned, you have to move away from 2.5 meters as much as you can. It's better to the shorter side, but it also works to the longer side. So IRI curling makes the slab length very critical in IRI. So this is a profile of that project I was telling you about. You can see the curling of the slab. That 8 feet slab or 7.5 feet slab was curled 2 millimeters on the edges. And here you can say, sorry, it's in Spanish, slab length in meters. So there's an optimum. When you run it through ProValves with the software, there's an optimum where you get less IRI for the same profile, just adding or not the curling. So we've learned that. Shorter slabs tend to have better IRI. Well, I talked about the geotextile. This is something that I think there was this is something here in the US copied from the Germans, and we copied from the people here in the US. But this is the original theory, just put geotextiles to reduce, as the interlayer to reduce water pressure. Fibers. Fibers, this is the testing we did in Champagne. At that time, my father didn't believe too much in fibers, so Professor Rossler forced us to put the last section with fibers. This was a synthetic fiber. So that's the difference. Those two pavements have exactly the same traffic. It's insane. So how well the fiber helped the amount of traffic. In the testing, and anybody wants to see it, it's available. It's a document that's available. I can send it to you. In this particular case, this pavement had 20 times more passes than this one for the same cracking. So fibers really work. When I talk about fibers in fatigue, this is all fatigue, there's two basic performances of fiber when you have deflection hardening and when you have deflection softening, like the blue line. So everything I'm going to talk is deflection softening. It's with low volumes of fiber, okay? Because if I don't say this, people complain and say, hey, but my fiber does something different. Okay, that's fine, and it could. But I'm just talking about this particular behavior. So one of the things we've learned is that fibers work really well when you have bottom-up cracks. And they work really well because it's not only the fiber that's holding the crack together, it's the confinement of the soil that's pushing back up, and it's the friction. So when you have bottom-up cracks, friction, fiber, concrete, and confinement make that the energy to make that crack advance very high. So short slabs, by design, always fail bottom up because they're cut on the top so that you don't have that failure mode. So what it does is when you add fibers into this, it uses the best of both worlds, basically. So we've done measurements. The first pavement was built 2011 in road pavement. So we did all this. Again, this is a study that if anybody wants it. So different design, those are easels, different thicknesses, if it has fiber or not. At the beginning, they didn't have, and now we've used fiber in all of them. and so forth. So I'll just give, so what we did, we measured with laser profiling, IRI and faulting, and to measure cracking every certain amount of time, what we did was we invented a way of measuring cracking with a GoPro camera. So we take a picture of the pavement every 1 second, and we measure the cracking in those 6 slabs in front of the car. It has worked really well, and you can really measure cracking with that. The resolutions of the camera is amazing, so it works really well. So just to go through it, look, that's one example of how good the picture is. So what we've been doing is comparing results with the software performance. Okay, so we've done that for that's IRI. This is cracking. So just to go for it because of the time, so different projects, and this is a very interesting one, and I'll be very fast on it. This is one road that it's in a place in Chile where there's nothing. There's nothing in between those two. So all the trucks that go over here go to Ushuaia, an Argentinian town down here. So what's interesting about this, it's the same contractor, it's the same pavement, it's the same base, it's the same climate, everything is the same. The only difference is one is 14 short slabs, fiber reinforced, and the other is 20 centimeters designed by Ashton 98, 4-meter slab. So that's where it is, so that you have a grasp. So it's completely opposite from where we are now. We're up here, it's down there. And that's the IRI of the short 14-centimeter short slabs, and that's the IRI of the 4-meter, 20-centimeter or 8 inches long slab. So the short slab is 6 centimeters thinner, and it's performing better, not only in IRI, but in cracking also. So the thickness paradigm, we have equivalent structures that costed less, actually, the short slabs, and they're performing better with a thinner pavement. So just as a summary, for the different projects, this is the calculated IRI, that's a measured one, it complies every time. And in the cracking, it's the same, apart from this particular project, which is still very close. Okay? So the last thing, and it's take me 2 minutes. We've extended this to low volume roads. As Jim was saying, the easiest thing is to just leave it gravel. That's the most cost effective in terms of initial cost. But the maintenance is very high. The option we normally use in South America is double asphalt treatments. Just put a layer of stone and then just a small layer of asphalt on top. So what we said is that you have the road, so if you have trucks and cars over it, it's good enough for what I'm going to say. So when you have that, that's the pressure over that existing subgrade. This is just a scheme, it's not, it's trying to show the effect. So what normally people do is put a granular base, very high CBR, and an asphalt layer, so that makes it better for the road. The stresses are lower. But now, if you put concrete directly over that, the stresses are even lower. So why don't we do that normally? And it's because concrete doesn't like uneven surfaces. It cracks. But fiber-reinforced concrete doesn't mind that much. So what we came up with is we extended the calibration on OptiPave, doing a lot of different test sites. All these pavements you're looking here are somewhere between 2.5 inches and 4 inches. And we put that level of traffic over them. They didn't last too long. They were not meant to last too long, so it was an accelerated testing in a known condition. So with that, we recalibrated or checked OptiPave, and OptiPave was able to predict up to 2.5 inches with fiber-reinforced concrete. So that's part of the dots I showed you up there. So what we're proposing on this is having roads like that, parking lots, anything that is stable, you can come and pave it, and this particular one, that's 3.5 inches, that's an error there. We just pave it with 3.5 fiber-reinforced concrete on top. That project today was designed for 5 years, because that's what the asphalt treatments last, and they cost more or less the same. But this project is now 11 years, and it's still working. So just as an example, and I just have a couple of slides more. So this project here was built asphalt and concrete in the same project. So the government said, okay, we'll build from here to there in concrete and back here in asphalt. And these two pictures are, I don't know, 10 feet apart. So it's just the failure mode. I just wanted to show on an even example what the failure mode was going to be. And that's the failure mode on this asphalt, we've all seen that, and that's the failure mode on the concrete. So in terms of serviceability, you have to come back and do something to that. You don't have to come back and do something to this. So in this case, the ministry in Chile decided to just leave it there over the 5 years to see what will happen. So that this happened at about 3 years of construction. So concrete doesn't like uneven surfaces, but it cracks, and the cracks worked very well when it has fiber in it. And that's the worst picture I could find, with 60% more of the design life. So this was designed for 5 years, and this was 8 years old. And that's the worst crack. So what we are saying is that if you allow cracks on the pavement, you can extend the life of this. So you just replace a couple of slabs, and you will have a completely functional pavement. And we're doing that in many places. So that's the software, that's the prediction of the software, and that's the real life situation. So we designed these for 50% of slabs cracked, because we're assuming the life of the pavement is after it starts cracking as well. This is not a highway, this is a low volume road. So I think this is a really interesting solution for countries that have a lot of gravel road. Just some examples, different places. These are normally built locally, just local people, we train them and they just go and build it, very easy. It's not the best looking pavement, obviously, it doesn't have all the standards, and it's not meant to be. It's meant to be a low volume road that will replace a gravel road. Just different applications. This is in a very rainy area. You see the thin blade, you almost don't see it, it's so thin. And a different one. This is in the very south as well. Just different solutions for the same blade. Thank you, just in time.